In this video, I'm going to derive a method for calculating the hydraulic thrust on submerged plane surfaces. We're going to assume some fundamentals. First, since hydrostatics considers fluids at rest, there's no shear stress, which means that all the forces on a body in the fluid are normal to its surfaces. Second, that we have a hydrostatic pressure distribution, meaning that pressure increases linearly with depth with gradient ρ times g, where ρ is the density of the fluid and g is acceleration due to gravity. Here, the grey arrows represent the magnitude of the pressure at different depths. This linear distribution, often represented as a pressure diagram as shown here, is the basis for calculating the hydraulic thrust on submerged surfaces. Suppose we have a plane surface which is submerged in a fluid. To help with visualization, let's mark the line where the fluid intersects with the surface and label it OO. To define the hydraulic thrust, we need to know its magnitude, direction, and point of application. We know that the hydrostatic pressure is perpendicular to the plane surface, so the resulting force is also perpendicular to the plane surface. The point of application of the hydraulic thrust is called the centre of pressure, and we usually denote it C. The centre of pressure is defined as the point of application of the hydraulic thrust F, which produces the same rotational momentum effect around the axis OO as the distributed hydrostatic pressure over the surface of interest. Representing this type of problem in 3D is difficult in general, so we adopt an alternative representation of this layout by looking at two views. One view is a projection of the surface looked at square on, in the plane of the surface as shown here. This is then combined with a side view, perpendicular to the plane surface, so that our diagram looks like this. We do of course know what the pressure distribution looks like over the surface. The pressure increases linearly with pressure head with gradient ρ times g. Thus, we will have a trapezoidal pressure diagram, as shown here. To find the hydraulic thrust, we need to integrate the pressure over the surface of interest. In the case of a rectangle, this is straightforward, but here I'm going to derive a method for a general case so that we can deal with surfaces with a variety of shapes. Let's consider an irregular area A on a plane surface inclined to the free surface of a liquid. Let G be the centre of gravity of area A. Let x bar denote the distance of G from OO, and let h bar be the pressure head at G. We know simply from the geometry that h bar equals x bar sine theta, where theta is the angle between the plane surface and the horizontal. Consider an elementary area dA, which is a distant x from OO, and has a corresponding pressure head of h, and let dF be the elementary force acting on dA. We have h equals x sine theta, and dF is pressure times area, which gives us ρgh dA. We need to integrate over the area A to find the magnitude of the thrust. Noting that ρg and sine theta are all constants, we have ρg sine theta times the integral over A of x dA. This can be written in terms of x bar, the centre of gravity of A, since x bar times A equals the integral of x dA by definition. Thus, F can be written ρg sine theta times x bar times A. We also know that sine theta times x bar is the pressure head at G, which we denoted h bar. Thus, we have ρg h bar times A. Finally, we note that ρg h bar is the pressure at the point G. Thus, F simplifies to pressure at the centre of gravity times area. Okay, so we have the magnitude of the hydraulic thrust, but we don't know where its line of action is. It won't act through the centre of gravity since the pressures below G are greater than those above G. Thus, we need to find the point for which a force with magnitude Pg times A acting at that point would result in the same moment about the OO axis as the moment generated by the pressures acting over A. This point is the centre of pressure I defined earlier, labelled C on the diagram. Let x0 be the distance from OO to the centre of pressure of A, and h0 be the pressure head at that point. The moment of the elementary force dF about OO is x times dF, and integrating this over A should produce a moment equal to the thrust times the distance of the line of action of F from OO, which is x0. Thus we have Fx0 equals the integral over A of x dF. Substituting our expression for dF into the integral, we get Fx0 equals rho g sine theta I0, where I0 is the second moment of area of A about OO, defined as x squared dA integrated over A. I don't intend to go into evaluating the second moment of area here. It is something you can look up elsewhere. For a general shape, it's not trivial to find. However, for common shapes, there are standard results we can use. Second moments of area about the centre of gravity are given here for a rectangle, triangle and circle as examples. It's also useful to know the parallel axis rule given here, which again I won't go into any further as it is a standard mathematical result. Coming back to our irregular area A, we established that Fx0 equals rho g sine theta times I0, and earlier we found that the magnitude of the thrust F is rho g sine theta x bar times A. Thus we can find an expression for x0 in terms of the second moment of area about OO, x bar and A. We can apply the parallel axis rule I just mentioned to rewrite x0 in terms of the second moment of area about the centre of gravity, x bar and A. We can use this equation directly, or we can rewrite it in terms of pressure head. We know that h0 equals x0 times sine theta. Substituting for x0, we have x bar sine theta plus ig sine theta over ax bar. Finally, noting that x bar sine theta is h bar, we get the formula h0 equals h bar plus ig sine squared theta over ah bar. We can see from these equations that the centre of pressure is always below the centre of gravity of a plane surface, which is as we expected, since we know that pressure increases with depth. We now have everything we need to determine the hydraulic thrust on a plane surface. The magnitude of the thrust is given by the pressure at the centre of gravity times the area, or rho g h bar times A. Its direction is perpendicular to the plane, and its line of action acts through the centre of pressure C, the position of which is given by a distance from OO, x0, or the pressure head at C, h0. Let's look at an example. Suppose we have a reservoir of water with a circular gate lying on a plane at an angle 60 degrees to the horizontal. The circle has diameter 1.3 metres and its centre of gravity is 2 metres below the surface of the water. We want to determine the hydraulic thrust on the gate. Well, the pressure at the centre of gravity is rho g h bar, and taking the density of water to be 1000 kilograms per metre cubed, we have 1000 times 9.81 times 2, which is 19,620 pascals. The area in question is a circle, so we have an area of pi times d squared over 4, where d is the diameter of the circle, which gives us 1.327 metres squared. This gives us a force of 26,042 newtons, or 26 kilonewtons. So, we have the magnitude of the thrust, and we know that the direction of the thrust is perpendicular to the plane. So all we have left to find is the centre of pressure. The second moment of area about the centre of gravity for a circle is given by pi d to the 4th over 64, and sine squared theta equals 3/4 in this case. Thus, we have everything we need to substitute into the formula for H0, and we find that the centre of pressure is 2.04 meters below the water surface. This method, sometimes described as the direct formula method, can be applied to any plane surface.